Hello! In this video we'll continue to study the response of dynamical systems using octave, now by adding damping to our system. Let's see first how our equations look like. We'll continue to use the representation of a block with mass m moving in the horizontal direction, which here we are calling x. And this block is attached to a spring with coefficient k, and an energy dissipation device, which here we are representing as a viscous damper with coefficient c. We will also continue to use Newton's second law to reach the equations of motion for our system, and we can write Newton's second law as such. Now, the sum of forces we have in our acting in our system will be both the elastic force, which we saw before, and now we have also the viscous damping force, which you can write like so. If we pass all the terms to the same side of the equation, we get this classical representation of the equation of a block spring damper system. Before we go on trying to solve this equation, we're going to rewrite it using a few terms to make it a dimensional equation or non-dimensional equation. We've seen before this term the natural frequency, which is the square root of k over m. We'll also be using this term, which we'll call this Greek letter zeta, which is the ratio of the damping in our system over the critical damping for our system, where critical damping is given by this expression here. If we plug in these two terms into our equation, we can rewrite it as something like this. And with the equation written like so, we can go back to some calculus course or any dynamics book to check that the solution will look something like this expression here, with two terms c1 and c2 times these exponentials, in which we have both the zeta and omega n somewhere in there. And to solve for these constants c1 and c2 that we have in our equation, so to define it completely, we have to remember that we have three cases that can happen with this damping factor zeta. First, it can be less than 1 or between 0 and 1, and that's what we'll call the underdamped solution. If we consider zeta as less than 1 and go on to try to find our constants, we'll find this expression for our response in x of this system. So we have the initial conditions for displacement x0 and for velocity x0 dot, and we have our terms omega n and zeta in here, and we have a new term which is our damped natural frequency, which is given by this expression here, which also depends on zeta and the natural frequency. So you see that it is a correction that we have on the undamped natural frequency omega n, and that will be the frequency of the response of our system, as we see here in the cosine and sine terms. The second case happens when we have zeta equals 1, and that gives us the critically damped response for our system. And when we consider zeta equaling 1 in our equation, we'll find the constant c1 and c2 such that our equation looks like this. And the third case happens when zeta is greater than 1, and that gives us our overdamped response for our system. Considering zeta greater than 1 in this equation, we'll find the constant c1 and c2 looking like this, and if we plug these values in our equation, we'll get our final response for our system. It's a bit longer equation, but that's a brief revision for these three types of response for a damped system. So let's go on and start writing these equations into octave. I will start with the underdamped case, so going back here to this case with zeta less than 1, with the equations as written here. And now we're going to have a separate function so we can choose which one of these three cases we are going to use, obviously depending on the value of zeta that we want to see the response for. So let's start simply by writing these three equations and then trying to see what we can do to choose which case we are on. So let's start by simply writing all these terms as we have it here. So we have the exponential times the two terms in cosine and sine for our equation. Just be careful that now we have omega n and omega d. So all that divided by our damped frequency omega d, and then finally times sine of our damped natural frequency. So that's our first expression. That's our response, or our underdamped response, and that will happen when zeta is less than 1, or more precisely when zeta is between 0 and 1. Then we can go on to write our second case when zeta equals 1, which is our critically damped response. And you will see that you can simply copy the expression that is in our line 4, as a few terms will vanish in consequence to zeta being 1. So if we just copy this expression here below, we'll see that this term vanishes, so we end up with only x0, and in here we'll end up with only x0 dot plus omega n times x0, finally times t, like so. Actually, this term here and vanishes as well. Now, this is our expression for the critically damped response. And finally, we have the case with zeta greater than 1, or the overdamped response. So zeta greater than 1, and I'll just copy the response here to save us some time. Now that we have these three expressions here, we need to find a way to check which one we are going to use, and that obviously will depend on the value of zeta. But remember also that we have the expression from the previous video of the undamped response. So when we didn't have any damping, so which will be when zeta equals 0, which was this expression, as I said, when we used it in the previous video. So supposing we already have this value of zeta, we can assume we chose it somewhere. We can use some if statements and else if statements for us to choose which case we're going to use. So for example, if we have set this value of zeta somewhere, we can compare if the zeta equals 0, we're going to do this part here, and we can use an else if command to check if zeta is greater than 0 and zeta is less than 1, for which we're going to use this expression here. And we can go on building our nested ifs and else ifs for the other cases as well. And finally, if zeta is greater than 1, we'll have the overdamped case. So this is our if structure to check which of the cases, which of the expressions we're going to use, depending obviously on the value of zeta. And we're going to use this inside a function that will do that for us outside of our main program, so we don't have all these expressions inside our script and it looks a bit more organized. So let's going to do that now. So to make the contents of this file a separate function, we'll start the file by using the keyword function, and we will have to choose what is the output of this function. We'll see that in a moment. We'll choose the scripted name for this function, so something like dynamic response, and we'll have to choose, or we have to describe what are the parameters that are going to be needed for this function to work correctly. These parameters, it's quite straightforward for us because it will be the natural frequency, the damping factor, and the initial conditions that we have for our system. So we don't have to pass the damped natural frequency because you can calculate that inside our function. And the response or the output of this function will be the actual value of x that we're going to pass. As in our response we're going to calculate this x for a specific period of time t, we'll need this time as a parameter of this function as well. So that's how our header of this function will look like. The parameters, the name of the function, and the output. And this is the content of the function. Given these parameters, it will calculate our response x depending on the value of zeta, choosing the correct function for that. Just before we go on, we need to do exactly as we mentioned. We need to calculate this omega d. If we go back here into our expression, we can use this exact expression here for calculating this parameter. So this is the square root of 1 minus zeta square times omega n. So with this we have our function. If we save it, we'll see that the name of the file has to be exactly the same name of our function as in the header here of the file. And also we need to save it exactly in the same folder that we're going to use it later to make things a bit more simple. So you'll see that Octave already chooses the name of the file based on the header of the function. Now we can start using this function in a script similar to what we used in the previous video, which is open right here. I will first rename this file just so we can start making some changes as to reflect that now we have damping in our system. So remember, we started the file by defining the parameters of our system. Let's not start by describing the dimensional parameters anymore. Let's start by describing the non-dimensional parameters, which were omega n. Remember that by using this expression here with the values we had before, it was something close to 3, and we'll decide what is the value for our zeta. Let's start by using a underdamped response. So let's remember that this is the natural frequency and this is our damping factor. We will continue using our step. Again, we're not calculating the non-dimensional parameters anymore. We're defining them in our program here. We'll need again our initial conditions for displacement and velocity, so we're not going to change anything here. And as well, our time is going to be very similar. What we'll have now is that we're not going to use the expressions in this file anymore. We're going to use that function that we just create. So to use that, we'll just call the name of our function and pass the parameters for it. Just be careful, it has to be exactly in the same order that we have in the header of the file, which I will just remind or check right now. So we have omega n, zeta, x0, x0 dot, and time. So they have to be in this exact order. Okay? The way we're going to plot our response also does not change. It will be exactly the same. We might have to adjust the axis if you change a few of these values, but that's we can check later. What we need to adjust here is that as we're not going to decide or define the dimensional parameters anymore, we can update this to show the non-dimensional parameters omega n and zeta. Like so. Again, for our initial conditions, things will be very similar. And if we go back to this switch structure in which we are using to assign functions to specific keys on the keyboard to increase or decrease values, again, we're not going to use the dimensional parameters, so we're going to use A and Z to increase and decrease the natural frequency, and I'm going to use S and X to increase and decrease the damping factor. Again, for the initial conditions in displacement and velocity, things are going to be the same. So let's go on and start changing this to reflect our new script in which we use directly the non-dimensional parameters. And also in these lines here, we're going to use our function again as we have here in the line before. So I'm just going to copy and paste this line here. So again, you see that we don't have the expressions written here anymore in our main file, so that leaves us with a bit more organized code, an organized file. It's a bit easier for us to understand what is going on and where things are. So we'll have to do that and know this for first 4 cases in our switch structure. So just make sure you catch all of the instance of mass and stiffness that we had before. Remember that here is going to use the damping factor zeta. Again, we don't need to update that, and we simply paste this. And finally the last one. Updating the text as well for zeta instead of k. So there we go. So just to remind us where this switch structure ends, we still have the increase and decrease of the initial conditions of displacement and velocity. And before we test our program, we need to go back here to our function to do one thing that I forgot, is that in these multiplications here, we need to check or we need to remind ourselves that these two terms here are vectors, as our t as holds all the values that we want for our time. So we need to tell MATLAB that we're going to do this multiplication element-wise, and it's not a matrix multiplication. So we need this dot multiplication here and in here as well, or else we'll have an error because of the dimensions of the vectors that we're trying to multiply. Now, if we go back here, we can check our script or our function by running this, and we see that we get a response here that starts from our initial condition on displacement that we set, which is 1. Again, as our initial condition on velocity, it starts with derivative equals 0, so it starts horizontally. and it has an oscillation, but as we have damping in our system, quite a strong damping, this amplitude decays rapidly to zero. And again, we can change these parameters as we have them here to see what is the consequence for that in our system. So if we increase our damping, we see that the oscillation dies out even faster, and to the point where we have overdamped system, so our zeta is greater than 1. If we go the opposite way, we decrease the damping, we'll see that our oscillations persist for longer and longer until we have or we go back to the system without any damping, so the oscillations just are just maintained like so. So we can play with our response regarding to damping like so, and also regarding to our natural frequency or our ratio of stiffness and mass, which you'll see that will make the system respond faster or slower as we increase or decrease our natural frequency.